given on convection heat transfer. The problem is given like this. Heat is being transferred by convection from water at 48 degrees centigrade to a glass plate whose surface, that is exposed to the water at 40 degrees centigrade. The thermal conductivity of water is 0.6 watts per meter Kelvin, and the thermal conductivity of glass is 1.2 watts per meter Kelvin. The spatial gradient of temperature in the water at the water glass interface is dt by dy is equal to 1 into 10 power 4 Kelvin per meter. The figure is also given here. This is glass. This is the junction, water. This is the y direction he has chosen. This is the temperature variation indicating inside the glass. This is the temperature variation inside the water. The plate is at 40 degrees centigrade. The value of the temperature gradient in the glass at the water glass interface in Kelvin per meter is A minus 2 into 10 power 4, B 0.0, C 0.5 into 10 power 4, D 2 into 10 power 4. Another question given in the same problem is, it's a linked answer question. The heat transfer coefficient H in watts per meter square Kelvin is A 0.0, 4.8, 6, D 750. Actually, by looking at the values of heat transfer coefficient given here, we could directly put the value of 750 if you are aware of what are the probable values of convection heat transfer coefficient, particularly when water is the coolant. I had already given the ranges of H earlier. If free convection in gases, it is 3 to 20, 25. If it is a forced convection in gases, is around 100 or 150 watts per meter square Kelvin. But it is a liquid involved here. Water is an excellent coolant. So the expected answer for heat transfer coefficient would be 750. We would also calculate and check this answer. First of all, let me do the first part of the problem. That is the value of the temperature gradient in the glass. solution could be given like this. Now in the y direction, temperature is increasing. That is how the direction of y given. So from Fourier law of conduction, Q is equal to minus K of the glass into area into dou T by dou Y. Because in this case temperature is increasing in the direction of Y, I don't have to write the minus here. I have to write otherwise one more minus here, I could guess. That should be equal to the K of the water into area of the plate into dou T by dou Y in water. This is dou T by dou Y in a glass. K of the water is given as 0.6. A and A get cancelled. What is the spatial gradient of temperature in water at junction? That is given as at the interface. What I mean to say, 1 into 10 power 4. Therefore, K of the glass is given as 1.2 dou T by dou Y in glass at interface. Therefore, dou T by dou Y is equal to, in glass, is equal to 0.5 into 10 power 4 Kelvin per meter. That is the answer C. Now looking at the second point there, how I take the help of Newton's law of cooling. From Newton's law of cooling, and Fourier law of conduction, if we combine HA, temperature of the glass minus temperature of the water, is equal to K of the water into area into dou T by dou Y spatial gradient in water. A and A get cancelled. K of the water is given as 0.6. Therefore, H is equal to K of the water into dou T by dou Y in water at interface divided by temperature of the glass minus temperature of the water. What is K of the water given? 0.6. Spatial gradient inside the water at junction is given as 1 into 10 power 4 divided by 40. Of course, there is a minus here. 40 minus 48. There is a minus here. Minus minus gets cancelled. We will get 750 watts per meter square Kelvin. Hence the problem. Now I shall give you a small objective question given in GATE 2001. Water, Prandtl number, it is approximately 6, flows over a flat plate which is heated over the entire length. Which one of the following relationship between the hydrodynamic boundary layer thickness delta and the thermal boundary layer thickness delta T is true. A. Delta T is greater than delta. Delta T is less than delta. Delta T is equal to delta. D cannot be predicted. The solution could be given like this. Prandtl number of water here is given as 6. Implies nu is much greater than alpha. Nu is 6 times greater than alpha because Prandtl number is given by nu by alpha. Nu tells about the diffusion of momentum transfer. Hence, if nu is much greater, the thickness of the hydrodynamic boundary layer will be larger because the viscous effects are felt farther out into the free stream if kinematic viscosity is much higher. In such case, delta is greater than delta T. Answer is B. As I already said, the Prandtl number gives the idea of the relative magnitudes of thermal boundary layer thickness and hydrodynamic boundary layer thickness. I shall do another problem given in GATE 2002. The properties of mercury at 300 K are density is equal to 13,529 kg per meter cube. Specific heat at constant pressure is 0.1393 kilojoule per kg Kelvin. Dynamic viscosity is equal to 0.1523 into 10 power minus 2 Newton second per meter square, and thermal conductivity is equal to 8.54 watt per meter Kelvin. The Prandtl number of mercury at 300 Kelvin is A 0.0248, 2.48, 24.8, 248. The solution could be given like this. Prandtl number is nu by alpha, nu by K by rho Cp, where alpha is thermal diffusivity. It comes to mu Cp by K. Mu is given as 0.1523 into 10 power minus 2. Cp should be written in joules. That is 0.1393 into 10 cube. Thermal conductivity is given as 8.54. The answer should be 0.0248. A is the answer. Please remember that when we are calculating Prandtl number, keep mu value in Pascal second, Cp value in joule per kg Kelvin, and conductivity value in watts per meter Kelvin. Hence the problem. Now I shall do a problem given in GATE 2003. Consider a laminar boundary layer over a heated flat plate. The free stream velocity is u infinity. At some distance x from the leading edge, the velocity boundary layer thickness is delta v, v for velocity, and thermal boundary layer thickness is delta T. If the Prandtl number is greater than 1 or unity, then A. Delta V is greater than delta T. B. Delta T is greater than delta V. C. Delta V is approximately equal to delta T. U infinity into x to the power of minus half d. Delta V is approximately equal to delta T x to the power of minus half. Here Prandtl number is clearly greater than 1 given, that means nu is greater than alpha, that means delta V should be greater than delta T. A is the answer. Since nu is greater than alpha, because Prandtl number is greater than 1, the hydrodynamic boundary layer thickness would be greater than thermal boundary layer, because momentum transfer or momentum diffusion rates is greater than heat diffusion rates. Alpha tells about heat diffusion rate, nu tells about momentum diffusion rate. Here Prandtl number is greater than 1, that means momentum diffusion is quicker than heat diffusion, that means viscous effects are felt farther into the free stream, that means delta is greater than delta T, since Prandtl number is greater than 1. Now I shall do another problem. Heat is lost from a 100 mm diameter steam pipe placed horizontally in ambient at 30 degrees Celsius. If the Nusselt number is 25 and thermal conductivity of air is 0.03 watts per meter Kelvin, then the heat transfer coefficient will be A. 7.5 watts per meter square Kelvin, B. 16.2 watts per meter square Kelvin, C. 25.2 watts per meter square Kelvin. D. 30 watts per meter square Kelvin. Here the solution could be given as Nusselt number is HD by K. Characteristic dimension is diameter of the cylinder. This is equal to given as 25. Therefore H is equal to 25 K by D. 25 into what is the conductivity of air? 0.03. Diameter of the cylinder is 100 divided by 1000, 0.1. Answer should be A. Another problem I consider. For laminar flow over a flat plate, the local heat transfer coefficient Hx varies as x to the power of minus half, where x is the distance from the leading edge, where x is 0 of plate. The ratio of average coefficient HA between the leading edge and some location A at x is equal to x on the plate to the local heat transfer coefficient Hx at A is A1, B2, C4, D8. We have already said the previous analysis. H average is integral 0 to L Hx dx divided by dx. This comes to twice of Hx. Answer is B. Another problem I consider objective problem. For flow over flat plate, the hydrodynamic boundary layer thickness is 0.5 mm. The dynamic viscosity is, that is mu value, 25 into 10 power minus 6 Pascal second. Specific heat is 2 kilojoule per kg Kelvin, and thermal conductivity is 0.05 watts per meter Kelvin. Then thermal boundary layer thickness will be A 0.1 mm, B 0.5 mm, C 1 mm, D 2 mm. The answer could be given as from the ratio delta T by delta is equal to 1 by 1.026 into PR to the power of minus 1 by 3. What is Prandtl number value here? That is 1 by 1.026 into mu Cp by K to the power of minus 1 by 3. Delta is given. What we have to calculate is delta T. Mu value is given in Pascal second. The only thing is specific heat we have to convert into the joules per kg Kelvin. Because while calculating Prandtl number, as I said earlier, we have to keep the specific heat only in joule per kg Kelvin. We know mu value, we know specific heat, 2000 joule per kg Kelvin. Conductivity is given as 0.05. Delta is given as 0.5 mm. Immediately we can calculate delta T. If Prandtl number is happen to be greater than 1, then obviously delta T would be lesser than delta as such. That's the problem. Now I shall do a matching problem on matching. List 1 gives type of heat transfer. List 2 tells about governing dimensionless parameter. On the left hand side we have A, that is forced convection, B natural convection, C combined free and forced convection, D unsteady conduction unsteady conduction with convection at surface. Right side number 1 Reynolds number, Grashof number and Prandtl number. 2 Reynolds number and Prandtl number. 3 Fourier modulus and Biot number. 4 Prandtl number and Grashof number. Grashof number is denoted as GR. Here in the forced convection we had seen earlier that Reynolds number and Prandtl number, that is A for 2. In the natural convection or free convection we would be talking about Grashof number and Prandtl number. Reynolds number would never appear in the natural convection. B for 4. Combined free and forced. In this case we see both Reynolds number and Grashof number and Prandtl number. C for 1. For unsteady state conduction we see the Fourier modulus and Biot number. We have to remember here that Grashof number is seen only in the free or natural convection, whereas in the forced convection, Grashof number is replaced by Reynolds number. In the forced convection, Reynolds number. In the free convection, it is Grashof number.